Hello, in this video we're going to be looking at solving the electric field from a point charge, which is a very common problem you'll see when you start getting into electricity and magnetism, and it can be a little tricky, but you can break it down into a three-step process, and as long as you follow these steps, you'll pretty much be okay. So there are three things that you need to do to find the electric field from a point charge. The first thing that you can do doesn't involve any math. You just find the direction of the electric field based on the charge and where you're looking. Secondly, you'll find the magnitude of the electric field through Coulomb's law. And then lastly, if you have or if you're looking at a point that's off axis, you have to use some trigonometry to get the electric field in its x and y components, and we'll use our trig ratios of the sines and cosines. So let's go through each of these and we'll do a couple examples. So first off, the direction of the electric field always points away from positive charges and towards negative charges, and so you may find it helpful just to draw these lines around each charge, and whenever you find the electric field from, say, multiple charges, you just treat each charge separately, individually, and then add up their effects at the end. But again, your field always points away from positive charges and towards negative charges. As far as the magnitude of the electric field, all you care about is what's the charge and how far away you're looking. And to make your math a little simpler, at the end, just leave things in terms of the electric constant K. You can always insert it in at the end. As with most physics problems, you want to avoid any of the numerics until the very end. You want to solve things symbolically if at all possible. And so again, all you care about is what's the charge and how far away you are from the field, or how far away you are from the charge. Then lastly, if you're looking at a point that's off axis from the charge, you're going to have to use some trigonometry to get the electric field in terms of its x and y components. Now the nice thing is the electric field vector points along the same direction as your displacement or position vector. So as long as you have the ratios of the sides of the triangles, you can get the ratios for the electric fields, because again, those angles are the same. So the cosine, which is always defined as the adjacent side over the hypotenuse, is going to equal the x distance over the overall distance r, and you have the same ratio going on for the x component of the field over the magnitude of the field. Now this isn't to say that x equals ex and r is equal to e, it's that the ratios are the same. Likewise, when you look at the sine of an angle, sine is always equal to the opposite side over the hypotenuse, and that will equal the y distance over the overall distance r, and you have the same ratio for the y component of the field over the magnitude of the field. So let's look at some examples where we can apply these three steps. First, let's just do something simple. We'll have an electric field at a point directly, say, across from a charge, so we won't have to worry about y components or any trigonometry. So here we have a -7 Coulomb charge, and we're going to look at the location for the field 4 meters to the left of it. So the first thing that we'll do, again, don't worry about any math, is just figure out the direction of the field. Well, we have a negative charge. The field is always pointing towards a negative charge, so you can picture rays of light going into this negative charge. If we're looking at a location to the left of this charge, the field is always pointing towards that negative charge, so when we're looking at a location to the left of it, our field is going to the right towards that negative charge, which would be in the plus x direction. Likewise, if we were looking at a point over here, the field would be going to the left in the minus x direction. But again, we have a negative charge, the field is always pointing towards it. And so when we're over at this location, the electric field is pointing to the right in the plus x direction. So now let's look at the magnitude, which is the absolute value of kq over r squared. We take the absolute value, we can ignore the negative sign. We already incorporated the negative sign when we found the direction of the electric field. So we have a 7 coulomb charge. We're looking at a distance of 4 away from it. So we have 7 over 4 squared, or 7 over 16k. And again, you can just leave things in terms of k for now. That's just a scaling constant in the end. So that's not so bad when we have a point on axis, because we don't have any y components. Our electric field's only pointing in the plus x direction, so the overall field is plus 7 over 16k in the x direction. So again, we first find the direction of the field, then the magnitude, and since it was at a point on axis, we didn't have to worry about any trig ratios. But now let's consider an occasion where we're looking at a location off axis from the charge. So let's say we have a plus 11 coulomb charge, and we're going to look at a location 4 meters to the left of it and 3 meters up. So we're going to have both x and y components running around. So the first step, just worry about the direction of the field. Well, since we have a positive charge, the field is always pointing away from that charge, so you can picture rays of light coming out of that positive charge. And so since we're looking at a location up and to the left of it, our field is pointing away from that positive charge. The field is going up and to the left. So up would be in the plus y direction, and left would be in the minus x direction. So we're going to have x and y components to our field. So we have the direction now. Next step is to get the magnitude. The magnitude goes like kq over r squared. So we need that overall distance from the charge to where we want to find the field r, which we can do just with the Pythagorean theorem. It would be x squared plus y squared all under the square root. So we have 4 squared and then 3 squared. We'll end up with an overall distance of 5 between the charge and where we want to find the field. So we do the magnitude of the field, kq over r squared, would be k times 11 over 5 squared, to end up with 11 over 25k for the magnitude. Now the last step is where it gets tricky. This is where we're going to have to apply our trig ratios to get the x and y components of the field. But one thing to point out here is we note that since we have a positive charge, the field is pointing straight away from the charge. So this vector that points from the charge to the location has the same direction as the electric field vector going directly away from that charge. And we're going to take advantage of that for our trig ratios. So you can picture just 2 triangles going on here. We have one triangle is our displacement or position vector, and then one triangle is our electric field vector. And they're both going along the same direction because our field is going directly away from this positive charge. So when we look at our trig ratios, this angle is the exact same as this angle, so that means their sine and cosines are going to have the same value. And so we can use our sines and cosines to get the x and y components of the field. So first let's look at our x component. Well, cosine is always defined as the adjacent side over the hypotenuse. So in our position or displacement vector, cosine would be the adjacent 4 meters over the hypotenuse 5 meters, and you're going to have the same ratio of ex over the magnitude of e because you have the same angle describing them. So we have cosine of theta is x over r. That's the same ratio as ex over the magnitude of e. So if we multiply both sides by the magnitude of e, we get ex is equal to x over r times the magnitude of e, and we have all those values. We'd have 4/5 times 11 over 25k, which is 44 over 125k. And we'll do the same methods to get the y component of the field. We'll use sine. Sine is always defined as the opposite side over the hypotenuse. So in our position vector, the opposite side of this angle is y, 3 meters over our hypotenuse r, 5 meters. And we have the same angle up here in our electric field triangle, where the opposite of this is EY, and the hypotenuse is magnitude of E. So the sine theta ratio in our position vector is y over r. We have the same ratio as EY over the magnitude of E. If we multiply both sides by the magnitude of E, we get EY is equal to y over r times the magnitude of E, which is 3/5 times 11 over 25k, which is 33 over 125k. Again, the key thing to note here is because our electric field vector points along the same direction as our displacement or position vector, we have the same angle describing both vectors, both triangles. So that means their ratios, or the trigonometric ratios, are going to be the same. So cosine of theta is x over r, that's the same ratio as ex over the magnitude of E. And sine of theta, which in our position vector is y over r, has the same ratio as ey over the magnitude of E. Last thing that we'll do is we'll put in these values for ex and ey with our directions that we found in the first step. So we had our electric field pointing away from that positive charge is going up, which is positive in y, and left, which is negative in x. We'll have our x component, which is negative in x minus 44 over 125k in x, and then a positive y component plus 33 over 125k in y. Again, the three-step process that you use to find the electric field at an angle, first, don't worry about any math, just figure out the direction of the field. It's just based on whether the charge is positive or negative and where you are in relation to the charge. The field always points away from positive charges and towards negative charges. Second step, you figure out the magnitude of the electric field, which is the absolute value of kq over r squared. So you just care about whatever the charge is and how far away you are from that charge. And then lastly, if you're looking at a point off angle, you'll have to use your trig ratios to find those x and y components of the field. And because your position vector points along the same direction as your electric field vector, your trig ratios are going to be the same for each of them. So cosine of theta, which is equal to x over r, is the same ratio as ex over the magnitude of E. And sine of theta, which is y over r, is the same ratio as ey over the magnitude of E. So I hope you found this video helpful. I'll be posting some more in the days to come.